Hi, in this video we will walk through the architecture documentation of a demo marketplace. This will be a semi-technical discussion, but we won't be discussing code. Our goal is to simulate an average day of work in a software company to demonstrate how Team Veda addresses the challenges. It's okay if you're not familiar with all the technical terms, we will try to explain it on the way. We have discussed the philosophy and usage of Team Veda in other videos, but let's recap the basics before we get into the demo. Team Veda is a knowledge base that specializes in documenting software architecture. Conventionally, software architecture has been documented as a mix of freestyle text and diagrams scattered across many folders and managed by different teams. Team Veda introduces the concept of a modular documentation organized as a collaborative graph. A graph, as we know, is a set of connected nodes. All interdependent software systems within an organization are connected as a graph. What's even better, the subcomponents within each software system are also connected as a graph. This is what makes graphs a perfect fit for documenting the backing software systems and mapped closely to the code. The nodes in our graph are called Veda modules, Veda meaning knowledge in Sanskrit. These modules document the essence of a given software component, like the system inputs and outputs, summarized implementation details as a series of steps, and design constraints such as cost, time, and performance, as well as context like dependencies and consumers. The edges of the graph document connection information such as data exchanged between two software modules, like the nature of dependency and the intent and metrics for that data exchange. This graph is commonly known as software architecture or the blueprint of an organization's knowledge. Even for startups, this knowledge base is pretty large and evolves so fast that most teams cannot catch up. This results in pointless meetings and unintended bugs that should not have happened if we had accessible and up to date documentation. With these principles in mind, let's see if we can model an online marketplace for minting, buying, and selling NFTs. Before we get technical, please note we are not affiliated or biased towards the technologies discussed here. This demo just focuses on how to document architecture. It's not a system design tutorial or a design recommendation. We do not have any experience in the blockchain domain, and because this is an oversimplified architecture, there may be some technical gaps. We may rush through some sections to keep it short. The true test of our platform is to help self-learners new to a team or technology navigate their organization's architecture without hand-holding or narration. So a narrated demo is not the best use of our platform, but once you join the workspace, you can explore the details at your own pace. This demo is split into multiple sections. We will review the architecture first and then see how this graph helps resolve bugs and plan software releases. So jump to the later sections if you're not interested in the technical bits. Here's a quick primer if you are unfamiliar with NFTs. NFTs or non-fungible tokens are generally digital media assets like an image that can be considered unique or proved to exist in a limited quantity. Contrary to the popular opinion, the uniqueness of an NFT is not determined by the content, but instead guaranteed by the creator of the NFT. The process of creating an NFT is called minting. Since ownership of content drives the uniqueness of the NFT, the ownership records are typically stored on a decentralized ledger like blockchain and not a centralized database that can be changed by one party like a bank. The participants on a blockchain are identified by their public keys, and any transactions they do, like minting or selling the NFT, are signed by their private key to prove ownership. Since a user is defined by their public key and private key, these keys are typically stored on a wallet software. So think of public key as an advanced version of username, private key as password, and wallet as a password manager like a browser plugin. Wallet addresses are derived from the public key and serve like a dynamic bank account number for transactions like receiving or sending tokens instead of sending money. NFT Marketplace can be a website where users can mint and trade NFTs, just like we trade goods on marketplaces like eBay or Amazon. An artist can link their wallet to sign transactions. Then they can mint a token for some digital art they own by uploading the media and signing a blockchain transaction with their private key. They can list their NFT for sale on the marketplace. Other users identify the tokens you own or mint using your public key, And then users can buy that NFT by creating another blockchain transaction that transfers NFT ownership from the artist to the buyer, just like we transfer money from one bank account to another. Conventionally, we have used diagrams to present architecture for such platforms. For minting an NFT, the user interface, like a website, calls an API, which calls the blockchain node and database in a sequence. There may be a second team that works on the sell NFT feature that may use a different diagram like this. The challenge with these diagrams are that they are often out of sync with each other, as well as the code that they are supposed to represent. They are treated as a presentation tool and barely help the folks who are developing or debugging a feature. Now imagine if you're given these diagrams and asked to fix a certain issue in the API. This diagram does not even tell you where to begin. Let's see if Team Veda can optimize this experience. We can start from the list of teams and select something that indicates a visual entry point like the website, which has a dashboard UI feature. The dashboard feature is built of multiple visual and non-visual modules. Let us pick the UI module. The Marketplace dashboard view is an entry point to the website, which has links to other features like wallet linker, features for minting and searching for NFTs, etc. So for the demo, we'll focus mainly on the minting feature and how we can list the minted NFTs for sale. The first step is to link a wallet, which is a third-party browser plugin. We are not interested in the internals of the wallet. So it's just enough to know this module provides a wallet address that we need for other features to work. The data type is also documented here. On a high level, wallet generates a public key private key pair and saves the keys securely. A wallet address is derived from the public key to be used as the user identity for transactions. User is prompted to authorize the use of wallet with the marketplace website, and the wallet address is returned to the module consumers. Let's close this and move to the Mint UI module. This module is hosted at a different URL and maintained by a different team. The steps to mint are: get the media asset URL to be minted, verify the URL correctness, build a blockchain transaction, and publish it on the blockchain. This module depends on the publish asset UI module for the first step. The asset publisher module first reads the media asset and metadata for the NFT from another module, which is a form UI. This form module has declared which constraints it can process and what values it captures. The NFT name is a unique readable name for the NFT. Uploaded media is returned as a byte array. The media file uploaded by user is stored on a distributed file storage system. The form provides two popular options for storage, which is IPFS and Arweave. The NFT transaction can be executed on different blockchains, so this marketplace supports Cardano and Ethereum blockchains. The first step is to present a UI and get user inputs for those fields. Not all the data entered by the user is stored on the blockchain, as it increases the transaction cost. So some of it is stored in the marketplace database. The data published on the blockchain is generally referred as on-chain data, while the remaining is called off-chain data. Finally, this module returns the submitted data to its consumer, which is the asset publisher. Unlike the reader steps we saw in blue, the red line indicates that this module writes data to another module, which happens to be an API module that is hosted on GCP and maintained by a different team. This module upserts this data to the database module hosted on GCP Bigtable, and it stores the off-chain data, which is also called metadata. The database modules do not have an algorithm, and they generally have the same data in both incoming and outgoing contract. So here the NFT ID is marked as primary key. This metadata is read by another API that we will discuss shortly. So we know how publish asset module got the data it needed for the next step. Let's clean up this some space to make room. Storing media on a distributed storage network like IPFS is free, but Arweave costs money. So we need to calculate a storage fee and generate a unique transaction ID that will be used for subsequent steps. This module passes the fee details to another UI module that will now take care of charging the user. This UI library accepts cost, currency, transaction ID, and a callback function to return the result of fee payment. We won't be talking specifics of data to keep this demo light, but remember all the data is present as step input outputs and as connection request response. The module presents a form to the user and calls a payment partner API. Since this step can take a long time and the UI may lose network connection, so we added one more step that registers with an internal payment module. Let's walk through the flow. The external payment partner API module processes the payment, generates receipts, and calls the marketplace webhook server and passes the result. The webhook processor writes the payment status data to a queue, which is a traditional message bus like Google PubSub on the topic payment result. This queue is naturally a data store. So the payment status API module has registered itself as a subscriber for all the messages on that topic, and it reads the payment result from the queue. This API uses WebSocket, so its consumer will get the payment result as soon as this API receives it. Now, as we can see, the reader consumer is the payment UI module that triggered this flow and was waiting for the payment result. So finally, the library results returns the payment result to the asset publisher. If the fee is paid or the user chose a free storage type, we now need to upload the image on the corresponding storage network. This API serves as a common facade for both IPFS and RV, and finally returns the location URI of the uploaded media asset to the asset publisher module. We now have the URI of the asset stored on the network and the metadata like token name related to the asset. So we have everything we need from the minter user. Now the minting module can move on to the next step of building a blockchain transaction. The input to this step is the data uploaded by minter, and we expect an NFT transaction as an output. A transaction is just a data structure with the data fields that will be stored on the blockchain network. The transaction builder module is a facade that supports two blockchains depending on the user choice of Ethereum or Cardano. Because transactions are defined by a structure, they have standards for each network. Ethereum network uses a standard called ERC 721 for building NFT contract, while Cardano uses a SIP25 standard for transaction data structure. We won't be discussing Ethereum in this demo, so let's switch to Cardano. On Cardano, the first step in building a transaction is to generate a unique policy ID on the blockchain. This policy defines rules for minting and destroying the NFT. The policy module first generates a new set of keys and generates a policy script. We see commands written as part of the notes. We could also point readers to the full documentation or source code for these commands. Finally, this module returns a unique policy ID. Next step in building a transaction is to build a metadata script that declares what data goes on the blockchain and in what format. So the blockchain transactions, just like credit card transactions, have a fee that is paid by the transaction publisher to the network that validates the correctness of transaction. On Cardano, unlike other blockchains, this fee can be determined before submitting the transaction. So this step says the marketplace will pay that fee and not the minter. Just like banking transactions that transfer money from one account to other, this transaction is similar to creating money as a token, which is then deposited to minter's wallet address, which is like a bank account. The transaction is built using the fee, policy ID, token name, and asset location. The transaction is signed using the policy keys held by Marketplace as a proof of policy ownership. A digital signature is just a new data field that is added to the transaction body. This module finally returns a data object that declares the NFT metadata and associated rules for destroying the token as minting policy. The publisher module checks for blockchain type and passes the transaction to Cardano's specific publisher module. The policy we created earlier requires both the minter and marketplace to co-sign the transaction. This module prompts the user to sign with their private key and then pulls its private keys from a secure vault to sign. This will add two signatures to the transaction body. So the signed transaction is then returned to the publisher module. The algo prompts the minter to pay the transaction fees that was calculated earlier, and it adds the proof of payment as one more data field in the transaction. Finally, this module calls an API that will publish this transaction on the blockchain by executing a command which is a Cardano command line utility. The software used to interact with the Cardano blockchain is called Cardano Node. The Cardano node has a mempool, which is a queue for unpublished transactions, sort of like a staging area before the transaction is submitted to the chain. The Cardano blockchain is essentially a network of many computers running this Cardano node software. So other nodes read this transaction from the mempool of their peers and validate the transaction. The validated transactions are then bundled into a block by Cardano nodes that are called block producers. The block producers are randomly picked by network to build a block and then add it to the chain. Once the confirmed transactions are added to the blockchain, they are deleted from the mempool. Each Cardano node keeps all the blocks of transactions in a local database, in this case, a Postgres database. This is an equivalent of a distributed ledger, as all the blocks and transactions recorded in this database have been validated and verified by all the nodes participating in the network. We have an API module that reads this blockchain ledger module to query by wallet address of the minter and checks if the newly minted NFT token has been deposited to the wallet address. Do note that this is a highly simplified version of how blockchain transactions are processed. We will defer the blockchain internals for a future session. Now, since the NFT has been minted, let us revisit the dashboard module to see if how does the user sell this minted NFT. This UI module lists all the NFT transactions minted by the user and is accessible at this URL. The NFT list view module depends on an API module to get all the NFTs published by the current user. The UI module provides an input wallet address that is read from the wallet module we discussed previously, and it receives a list of transactions received on that wallet address. We also see field mapping because the same data is named differently between the API team and the UI team. The API module first tries to get some configuration properties from a configuration file that is hosted in a Google Cloud Storage bucket. These are dynamic configuration properties related to transaction processing. One of the outputs of this step is confirmation depth. We have seen how block producers add blocks to a blockchain. Blocks can also be rejected if a malicious block producer node adds a block. This means even if a transaction is added to a block, it can be rolled back unless sufficiently large number of subsequent blocks have been added to the chain for preventing a rollback. Now, the marketplace owners decide how many blocks should be added before they consider a transaction to be final. We call that number confirmation depth. You may recall during mint operation, some transactions were queued in a mempool before being confirmed, and some were published to the blockchain ledger. The API module reads data from the ledger and mempool and finally merges those into one list. The last step is to apply some logic to determine whether the transaction can be considered confirmed based on the confirmation depth value we just discussed. This data is finally returned to the consumer module of the NFT list view, which then allows the user to select an NFT transaction to see its details. Going by the label, we see this detail view is embedded within the list view itself, and it is receiving some data from the consumer list view. This data is the wallet address, token name, and whether the transaction is confirmed. The NFT detail module may need some more data that we stored off-chain, which is fetched from the metadata database using an API. So we apply some additional business logic to decide whether we can allow the user to sell the NFT, and lastly, this module displays the full metadata. So the NFT detail module can then create a sale transaction similar to what we have already seen in the NFT minting process. So that kind of sums up the overall architecture, but let's explore some more aspects of this graph. While exploring the graph, you may have noticed all the modules directly connect to other modules. This works from a functional perspective, but technically that may not be accurate all the time. So this UI module connects to an API module, but the data does not directly reach the API. It generally goes through an API gateway. We use a gateway feature for representing interceptors that do not directly contribute to the application logic. The API gateway module resolves IP address using a DNS resolver, then delegates to a layer 7 load balancer, which routes traffic based on the IP address and distributes the traffic between different VMs. In this example, the gateway feature also contributes to some application logic, like transforming the request headers for conducting A/B tests. To be clear, gateway features are not limited to API modules only. Here, the UI module also depends on a gateway feature, like a dependency injection provider that provides A/B test values. It can also provide other configurations. It is also worth noting that this workspace is not limited to just one graph. We can have multiple graphs in the same workspace for, say, low-level designs that are even more closer to the code. Or we can have dedicated flows for certain business use cases with varying abstractions. So instead of maintaining separate low-level and high-level diagrams, readers can generate hybrid diagrams by mixing low-level and high-level documentation modules. We are avoiding code discussions in this demo, but let's briefly touch upon an iOS module. The Marketplace iOS team documents app-specific design. Now, this is an iOS module for the NFT list we discussed for web. This Vue module first gets the dependency from a dependency injection module that is linked as a gateway feature. If a UI module needs authentication as a prerequisite, we could have also added another gateway feature for authentication. In the next step, this view links a Vue module to get the NFT list and navigate to the NFT detail module. The Vue module algorithm describes the steps taken to fetch data from the API. And similarly, the network feature is linked as a gateway, and it offers HTTP client and related configuration. So assuming we have a good understanding of the marketplace architecture, let's review how this helps readers from different teams and in different roles. You may have noticed that the data fields are first-class citizens on our documentation platform. This helps us develop new productivity tools. For example, the user experience team may want to know the data format and the maximum length of this asset name for redesigning the NFT detail view. Instead of setting up meetings with engineering partners for every idea, what if UX teams could find the source on their own? Now, this allows quick design iterations and up-to-date information directly from the source, skipping the intermediate teams. Now, data in each module is either provided by consumers, pulled from dependencies, or generated in the same module using some logic on the data received from the consumers and dependencies. On our platform, our dependencies are considered downstream and consumers are considered upstream, irrespective of the read or write operation. The NFT detail UI has only one step that depends on the other module, the NFT detail API, which apparently does not return the asset name we are interested in. So because detail UI is embedded in the list view, perhaps this data is being passed from the upstream list view with a different name. Looks like it does, but the team uses a different name. Now the data field mappings on each connection capture the difference in naming across multiple teams. Now since we know the list view module offers the data to the detail module, we can check for downstream and upstream connections of list view module and repeat this operation until we find the source of truth for this asset name. Now this is a huge time saver compared to meetings, but it still requires some effort. So a better alternative is to use the field tracing tool, which helps you trace the journey of data with much more convenience. So we start with the NFT detail module and look for downstream sources of asset name. And as we saw before, there are no downstream sources. So we switch to upstream and try finding a match. We also see the reason why this data was passed around. We continue the downstream journey until we hit a potential data source, which is either the local mempool queue or the ledger database. So you may notice while NFT listing team uses the phrase asset name, blockchain team uses the phrase token name for the same thing. Without field mappings, cross-team collaboration is often challenging because teams do not have a shared vocabulary to begin with. But moving on, what if we want to know who writes to the database? So let's continue upstream. We see another change of name. The blockchain publisher team uses the phrase NFT name. We finally reach the UI layer, which has no upstream or downstream source. We can check the module contract to find the rules imposed on data across all the systems and how different teams process it. We can also operate in the opposite direction. Data producers like an API or a database, they can track the flow of data to understand how each field is consumed, for example, by a user interface module. Let's switch to a scenario where your security team wants to audit the design changes. Now, with this graph, security architects can observe data exchange across all the systems, and they can also detect the vulnerable modules in the design phase itself. In the transaction submission module for Cardano, we see email data as an input. At the first look, this looks dubious, right? Because why does a blockchain transaction require email? Maybe we are leaking some personal information. But looking at the algo steps, we can understand this email is used for sending transaction notifications to the user and not really submitted on the chain. Security teams can also add attributes to the data that should be handled with care. Here, the email is being passed between different systems. Now, setting a PII attribute at the source of truth contract, that will help all the consumers take precaution not to expose the data either through logging or some other means. This connected graph also enables engineers to identify optimization paths in the design since they have access to a large scope and context, and that includes both dependencies and consumers. For example, the payment module has multiple consumers. We are charging the user twice, first for the asset storage and then later for publishing contract on the blockchain. Now, someone new to the team may question why can't we merge the two steps and charge the user upfront and then refund the difference if the blockchain transaction fails. So team members can also do a design proposal, chalking out a plan that shows all the affected modules with the proposed algorithm and data. We have covered design proposals separately. Check out the how-to video if you are interested. The design modules can also include summaries like KPIs and SLOs that define team success. This helps all the team members work towards a common set of goals specific to their role and to get a 360 view on how their work contributes towards the organization's roadmap. Metrics can be cost related, performance related, or timeline related. The UI modules will generally have different performance metrics from backend services. The connection between two modules are also bound by SLAs and can be separately documented. So the NFT sale view has metrics indicating an average click-through rate of 0.5. A higher CTR helps with higher revenue. So let's say a product manager recently joined the team and observes that this number has gone down to zero point 0.3 in the past few weeks. Instead of setting a meeting with engineers, he decides to do a root cause analysis first. So he notices the algorithm disables the sale button if NFT transaction is not confirmed on the blockchain yet. The inputs indicate a flag that seems to be coming from the NFT list module. The list view itself fetches this data from an API, which has a logic to set this flag based on the input transaction depth and the confirmation depth. So one possible cause of this bug is that transactions are taking too long to be confirmed on the blockchain, which is why the UI disables the sale option and thus reducing the click-through rate for that module. So we can see the first step of getting the confirmation depth from a configuration API that has a value of 50 blocks. So what if we could change the confirmation block depth from 50 down to 10? That will increase the risk of selling a transaction that is not yet confirmed, but it may also bump up the click-through rate. So the product manager can take this short-term decision as a fix and discuss better alternatives with a blockchain architect. Now, the architect sees that the API reads these transactions from a mempool, which is a queue. The queue holds unconfirmed transactions, and its metrics indicate that the average wait time of transaction is just 2 minutes. But let's assume that the team dashboard is showing 5 minutes delay. This means that the blockchain itself may be congested and acting slow. So what are the alternatives? The architect may propose integrating a new blockchain with faster confirmation times like Algorand, but the team first decides to do a cost-benefit analysis for such a major feature. The drop in click-through is impacting revenue that can be calculated given the right numbers here. We also observe integrating a new blockchain will take efforts by multiple teams like the blockchain team, the API team, and the UI teams. The graph makes it easy to visualize which modules need to change and who are the right SMEs for each layer as well. Since multiple modules are involved, we can now calculate a cumulative cost of development and plan the release much better by accounting for all the team estimates. Instead of running a self-hosted blockchain node, the architect can also propose using a cloud-based node service. So teams can estimate and plan the efforts using their previous learnings, for in this case, the Ethereum node service. So let's summarize the benefits before we wrap up this session by comparing this graph with sequence and block diagrams that we saw before. First and foremost, the Veda modules are mapped closely to code, like a class or a system that can be broken down into steps as functions. The design is also scalable, as each step and each module can be further broken down into modules that are executed locally or remotely. These modules are then composed to create a complex architecture. As a documentation summary, it addresses what an average reader wants to know quickly, and it's much easier to keep this graph updated therefore. This approach also helps standardize documentation and adapt good design practices like single responsibility or command query responsibility segregation. These patterns provide guidance when designing scalable event-driven systems. So we'll conclude this demo here with just one afterthought for you. Imagine you are starting a new company or just starting in a new team. If you are building the product or managing a team, will you prefer hundreds of diagrams and documentation pages, or would you like a consolidated graph like Team Veda? If your answer is Team Veda, this is a good time to try teamveda.com and get started. We are happy to be your knowledge partners.